louder. That's it. Clap for him. With the two factors mentioned, before it can be floating, you must have upthrust acting on it. That upthrust acting on it must be equal to the weight of the object itself. Am I communicating? Having known this, let's now quickly mention some of the floating objects we know, and you tell us why you think they are floating objects. That when we try to demonstrate or verify, we find it so. We find it to be floating objects. Can you quickly mention some of the floating? I've given this to you last week that floating objects are objects that are able to displace weight of fluid, that is upthrust. I need to say weight of liquid equal to its own weight. That means displace upthrust equal to its own weight. That's floating object. We can now quickly mention examples of floating objects. What are the examples? Ice block, yes. Ice block. Yes, which other one? There are so many you can mention. Ice block. We have football, table tennis ball, which you normally call egg. Tube. What do you say? Sheep. See? Talk loud and let's hear you. Somebody mentioned sheep. ETC. Now, let's quickly, having known, you can have more examples. Balloon, when you blow it, it's a floating object. So we can now go on to talk about principle of what? Flotation. Principle of flotation. Let somebody state what the principle of flotation is. We quickly want to see what's the principle of flotation. Anybody? I have given you the principle of flotation already. From what I have said earlier. And object, the principle of flotation says that when an object experiences upthrust equals to its own weight, it is said to be a floating object. Or you state it this way, put it this way, principle of flotation state that, that's another way of stating it, state that an object will float in a fluid. Of course, when we say fluid, we mean liquid or gas. You can put that in bracket. Liquid or gas. When the upthrust exerted upon it, by the fluid in which it floats, equal the weight of the object. I take it again. Principle of flotation states that an object will float in a fluid, open bracket, liquid or gas, close the bracket, when the upthrust exerted upon it by the fluid in which it floats equal the weight of the object. So that's the principle of flotation. What do we want to make across here? From this principle of flotation, we can conclude that weight of floating objects, equals to upthrust. That's according to the principle of flotation. So we can abbreviate this by simply saying weight of floating object, that is this, upthrust is U. So from here we can say weight of floating object equals upthrust. Call this equation 1. Then we know from what we have said earlier, upthrust can be determined by this expression. Density of the liquid, we learned that last class. Density of the liquid, volume of liquid displaced or fluid. Then G, acceleration. So, look at this expression. It's very similar to what I gave to you last week, but a bit different. This is, you can say, where, of course, you can say where WF equals weight of floating objects. Weight of floating objects. Then we have density. This is density of the fluid. Density of the fluid. Then you have volume. This is volume of the fluid. Volume of the fluid, and of course G is equals to acceleration due to gravity. Acceleration due to gravity. Now, I gave you an expression last class. If you remember, those of you that work on it, when we are talking about Archimedes. This is principle of flotation. But Archimedes in his own case said upthrust equals weight of liquid displaced. Upthrust equals weight of liquid displaced. That's according to Archimedes. And we break that was equation 1. We break this one into mg. Up thrust equals mg. That's equation 2. And we also break mass into density times volume times g. We refer to this as equation 3 as up thrust. Then equation 4, we said up thrust equals actual weight. Weight in air minus weight in fluid. Or actual weight minus apparent weight. Actual weight minus apparent weight. This one, the first 3 above, has to do with Archimedes. The idea comes from Archimedes. That means when you want to determine the up thrust, you need to know the volume of liquid displaced and you need to know the density of the liquid. With the two, an acceleration gravity is given to you, you can determine the up thrust, the object experienced in any fluid. But today, principle of flotation is telling us that the weight of floating object, equals the up thrust exerted upon it. Weight of floating object equals the up thrust exerted on it. That is according to principle of flotation. Why am I emphasizing this? This is where JAMB has its questions. So you relate this and this together. I will give you some examples. Then working examples and exercise. So you can determine the weight of floating object if the up thrust is known. The up thrust is equal to the weight of the floating object. When you get the weight of floating object, you can get the mass. What you need to do is to convert the weight to mass. You only need to divide by g to get the mass of floating object. They may make the question complex in WAEC that they will ask so many questions. Find the density of the floating object. When you have been told the up thrust, the object is the up thrust exerted upon the object. Indirectly, you have been given the weight of the object, and you can get the mass from the weight. They may now say, okay, calculate the volume of calculate the density of the object. If the volume of the object is this. So, all this, you expect questions like that. So, this is broken down into this. This and these are not the same, if you look at it very well, but they are very similar. So, that is that. Let's now see a working examples that have to do with floating object. At times, the object may be partially immersed before it floats. Like somebody mentioned ice block earlier. It is only 1/3 of the high block that will be above the water. It means 3/4 of the block will be immersed in the water. So you can determine the volume of that 3/4. If you know the volume of 3/4, you can know the volume of the whole height. If 3/4 of volume gives you certain amount, then you can find V itself to know the actual volume of the object. Now let's quickly look at example under this notation of object. Now example 1. And was half, an object was half immersed in a liquid of density 1150 kilogram per meter cubed, and displaced millimeter of the liquid. Calculate 1. Volume of the liquid. Calculate the volume of the object. Calculate the volume of the object 2. You have to calculate the upthrust. You have to calculate the upthrust exerted upon the object. Exerted on it. 3. Mass of the object. Then 4. Density of the object. Take G to be 10 meters per second squared. An object was half a mass in a liquid of density 1,150 kg per meter cube and displays 20 centimeter cubed of the liquid. Calculate the volume of the object. 2. Upthrust exerted upon the object. 3. Mass of the object. And 4. Density of the object. You can say exerted on the object. Yes. Who can solve the question for us in the class? Can you solve any of it? If yes, let me see your hands up. Yes? Yeah, come. Say. You raise up. Where's the doctor? I think one boy from Dr. Graham school stood up there. I've come back. There's nobody doctor. The whole of Dr. Graham school. Fast. Give it to you. They are coming to pick. Please clap for her. Although she's wrong, but at least she was not forced to come. That's why I really appreciate. I expect everyone, please give yourself dirty slap. Give yourself dirty slap. If what, and somebody is laughing, this is not a laughing issue. If you actually understood what we did last, those of you that were around the last class, I expect you to be able to do at least number one. I have reminded you that updraws equals weight of liquid displaced. According to who? Archimedes principle. Updraws equals to the weight of fluid displaced. And we break weight displaced to this. Then we are now talking of the information in the question saying the object was half immersed. So I expect you to say the volume of liquid displaced, which is of course 200 centimeter cubed, needs to be converted to meter cubed. Here it will become 200 all over 1 million. And that will become 2.0 times 10 raised to power minus 4 meter cubed. That is the volume of liquid displaced. This volume of liquid displaced will be equal to volume of half of the object. Volume of half of the object equals this. That's equal to 2.0 times 10 raised to the minus 4. Half of the object. So in other words, I expect you to say that half volume of objects will now be equal to 2.0 times 10 raised to the minus 4 meter cubed. Half of the volume of object was immersed. The volume of object that was immersed, the part of the object immersed, is equal to 200 centimeter cubes, which is converted to meter cube as 2.0 times 10 raised to the minus 4 meter cube. So, how do I get the volume of? You must have stated this, that volume of object, let it be this, is not known. That's what you are looking for. So, volume of object now, which is VO, will now become cross multiply 2 times 2.0 times 10 raised to the minus 4, which will now become 4.0 times 10 raised to the minus 4 meter cubed. Then if you want to have it in centimeter, you just, if half of the object was immersed and displaced 200 centimeter, if the whole had to be immersed, then it will displace 400 centimeter cube. Based on what you are taught last class, that I said it last class that how do you know your volume? I think one boy from here responded when I asked how do you determine your own density. You immerse yourself. Volume of the object immersed is equal to the volume of liquid displayed. So half of the object that is immersed, the volume of half is equal to the volume of the object displayed. Based on that, the whole volume, if it is immersed, it will be double the volume of the object. If half is 200, if all of them is immersed, that will be times 2. Do you understand? Yes, sir. Who said no? Let me see your hands up. Yes, what's the problem? I didn't use any of the formula because what is required does not need any of the formula. This is a simple thing. This is simple mathematics. Half of the object immersed and displaced 200. If the whole is immersed, what will be the volume of liquid displaced? Doesn't need any mathematical expression for that. Do we understand? No response? I don't understand what you are saying. If you don't, it means everything done during the camping, you don't understand. We did measurement and volume. I taught you how to determine volume there. And last week we talked about vol density. We also reversed to what we did during the camping. And you are here. You didn't say that was not clear to you. Today is only, if I say 3/4, if the volume is 3/4 is 200. 3/4. If I need the whole volume now, I should be able to do that. This is half. Half give the volume of 200. The whole will now give volume of 400. That's not a big deal. That's simple mathematics. Now we go to the second part of the question, which is Roman figure 2. We are to find the up thrust. We are to find the up thrust. I expect you to be able to do the second part, which is the up thrust. That's the formula on board. The formula 3 here give the up thrust. The formula 3 here give the up thrust. That's Roman figure 2 now. Roman figure 2 say find the up thrust. The up thrust U is not known. But you are taught that up thrust equals density of the liquid, volume of liquid displaced times G. That's the formula we use to get the second part straight away. When I say you can solve it, I know you have been given material, you have been given enough material that will enable you to solve it. So this expression here is here, and you are given last class. So up thrust is equal to this. So we are going to say, what is density of the liquid? Density of the liquid is 1,150. Volume of liquid displaced. Volume of liquid displaced is this. That's 2.0 times 10 raised by minus 4. G is 10. That's what you do to get the up thrust. And of course, up thrust is measured in Newton. So what we now do is to have it. You can simplify this. 10 raised by minus 4, 10 raised by 1. This will be minus 3 now. So you are having 2 times this, 0, 5. That's 0 again. 2 times this, 2 plus 1, 3. 2 times 10 raised by minus 3 Newton. That's what you are going to have. So you now refer this 1, 2, 3. So 2.3 times 10 raised by 3 times 10 raised by minus 3. So this and this cancel. Your final answer will be 2.3 Newton equals this. This is the up thrust. You are asked to calculate the up thrust. Everybody in the class should be able to do this. If you really understand what we did last class. Any questions on this? Is it clear to you? Now we move further. I have just said Roman figure 3, mass of the body. Now Roman figure 3, talking about mass of the object. Mass of the object, that's MO, not known. But according to the principle of flotation, according to the principle of flotation, the principle of flotation says up thrust equals weight of floating object. That was equation 1 given to you today. Up thrust equals the weight. And how do we get the weight? That's according to principle. We already gotten this. 2.3 equals mass of the floating object times G. G is 10. You can say M, let me turn this one to straight away. MFG times MFG. That's it. So the next thing is to divide both sides by 10. So you can conclude by saying mass of floating object is equals to 2.3 over 10. And that is 0.23 kilogram. 0.23 kilogram. That's the mass of floating object. In other words, that's the mass of object we are looking for. the mass of the object you are asked to calculate, that's the mass of object you are looking for, is the mass, that's 0.23. That's the mass of object. Finally, you are asked to find the density of the object. The density of the object. The density of the object. How do we get the density of the object? The density of the object will now be mass per volume. So now the last one, that's Roman figure 4. We need density of the object. The density of the object, D, not know. But we know this by saying mass of object all over volume of object. That gives the density of it. So the mass of object is just calculated to be, the mass of this one is just calculated to be 0.23 divided by the volume of the object. The volume of object is 4.0 times 10 raised to the minus 4 meter cube. This is kilogram, this is meter cube. Now you can express this in standard form. 2.3 times 10 raised to the minus 1 all over 4.0 times 10 raised to the minus 4. 10 raised to the minus 4 go up, become 10 raised to the 4. So we can have 2.3 all over 4 times 10 raised to the minus 1 times 10 raised to the 4. Because you have taken that one off, the minus goes. So this will now be 4 minus 1, that's 3. So you're having 2.3 times 10 raised to the 3 all over 4. So you can go on to simplify that. So we say 4 in 2, impossible. 4 in 23, that's 5, 20. Then you have 3. 4 in 30, that's 7. You see? That's 28. So you have 7, remainder 2. So press calculator and let's know what is it. 5, 5, 7, 5. 5 what?
5, 7, 5.
5, 7,
5.
Newton, kilogram per meter cube. That will be the density of the object. Is that clear? Now right, I'll give you another one. Right fast, I'll give you another working example before assignment. submission, those who go outside to stop taking notes. And you inside are murmuring. Is that not too bad? Yes. Who want to answer that? Yes. If I see you talking, I will ask you to excuse us. If you have something to say, you will give. You said? Yes, what you say?
You have to use volume of liquid, not volume of objects. You have a question, you have
Okay, that's a submission. Who else want to respond to that? I expect everybody to say something. Why did we use 2.0 times 10 to another instead of 4.0? You claim that it was class, you only the guests are talking. Yes, let me hear you. Who else want to contribute? So there is no boy in the class. Please clap for those that have responded and the person who has the question. I don't want you to deceive yourself when something is not clear and you claim it is clear. If actually that thing is clear, you won't allow her to end the question before you give the reasons. You are permitted to talk now. Only 2 girls were able to, and they contributed meaningfully. Well, the question to ask is very simple. We are using volume of liquid displaced, not the volume of the object. The volume of object is 4.0 times 10 to the minus 4. But we are making use to calculate the updraft. It has to be the volume of liquid displaced. Do you understand? We will have used 4.0 times 10 raised by minus 4 if the question say the object was immersed completely. If the object was immersed completely and we want to find the updraft on it, it will be total volume of object times the density of the liquid times this. But we are told that the object was half immersed. So the volume of liquid displaced will be equal to the volume of half of the object in the fluid. So we are making use of volume of liquid displaced, not the volume of the object. Is it clear to you now? So that is that. This is another question. An object of volume 60 centimeter cube was half a mass. Please, when I use half, I put half for easy calculation. It does not mean that every question will always be half. It can be 1/3, it can be 3/4, it can be any fraction. But I want it to be easier for us to calculate in the class. That's why I'm using half. Don't think that it must be half. Now, another question, if the half is not put, you'll be looking for half. They used to put half. Am I communicating? The first one includes half. This one is also half. Don't expect all questions will be half a mass. So this two was half a mass in water. We have to calculate the volume of water displaced. Then 2, across on the object. 3, mass of the object, very similar to the first one. If I may ask, who want to solve this question for us? Or can I call it class work?
Yes, sir.
How many of you can solve it? Let me see your hands up. Okay, I give you 2 to 3 minutes. Solve it and I will come to you to give me your own answer. I pause a bit. Solve and I will. Please clap for him. Now, what can you say to his work on board? You work something. Do you have the same answer with him?
No, sir.
What do you have to say? Who has something to say? Please answer your answer. If you have something to say, you quickly tell us. Are you not sure of yourself? We will appreciate you. Speak out what is in your mind. Yes.
That about two. That about two. And since doctors come to invest and volume of water.
Okay. You disagree with this?
Yes, sir.
What does it supposed to use? I don't say you should cross. Only one person is talking. I asked you to raise up your hand. She rose up her hand. Why are you crossing it? Yes. From which school is that? Ashero High School. Please clap for Ashero High School. The person working use the total volume of the object. You are not told that the object is completely immersed. We couldn't have used this. That's the question she asked earlier. That why did we use 4.0? And she was told that we didn't use 4.0 then because the object was not completely immersed. Here too, it was not completely immersed. Half of it is immersed. Half is above. You can only reckon with the part inside the liquid, inside the water, which is half. So it is half volume, which is volume of water display. He calculated the volume of water display, put it here, but he didn't work it out. Okay, he worked it out here, but he didn't use it. When you are asked to calculate the volume, so he only got the first one, which is the volume of the water display. Got this one right. This was wrong because the total volume of the object was used instead of volume of water display supposed to have been used here. Thank you. Any other observation? Anybody? Do you want to say something to the working? This is not the time for you to be writing. Stop writing and look straight to the board. I've given you enough time. Don't pretend writing something. Do you have something to say with what is on board? Let's listen to you. Number 3 also. What is wrong with number 3? Tell us what is wrong. Octros is equal to okay. Substitution was wrong, but the formula is okay, Abi. Alright. Yes. Are you raising up your hand? Number 4. Yes. Talk loud and let's hear you. Density of object, yes. The mass is wrong, but formula is right. Okay, clap for that. From which school? Okay, but Ashero responded to 2, corrected 2. Clap for them. Afro and Ashero. Now, I will say everybody should give yourself dirty slap first. Some of you cannot. I say give yourself dirty slap. You think I'm joking? That boy, stand up. Stand up. Not you, the one at the front. I said you give your dirty slap. Why you asked to give yourself dirty slap? Everything from beginning is not the way you are told to solve questions. So it means everybody would have made that mistake. What does this stand for? It was not defined. What does this stand for? Undefined. Every other parameter is undefined. Please and please. WAEC and NECO. You don't solve like this. Oh. JAMB does not know how you do your working. But WAEC and NECO will go through what you present. You are told to always start from concept. Of course, you start from concept. But nobody knows what each of these stand for. If you have not been told, I will not ask you to give yourself dirty slap. And I advise you then that every question, every calculation that comes your way, put that thing in mind and follow the procedure. You are giving the format, but you are not following. I asked you to come to the class with marker, every one of you. It's a test. When I came, more than 20 were in the class. We hardly found a marker. Keep it up. Now, the first thing what we expect you to do is to extract parameter given. And parameter you are asked to find, no mark is given to that. I have told you that. The first thing is to identify what and what you are giving and what you are asked to calculate. And the symbol you use to denote those things. It is after that you can now use the symbol alone. You have not introduced us to anything here. Once you write solution, the first thing you put solution, then you extract solution. Then what and what are we giving? Volume of the object. Volume of the object was given to be 60 centimeter cube. We divide by, so this will be 6.0 times 10 to the minus 5 meter cube. That is the volume of the object. So we can also talk about volume of water displaced. Volume of water displaced, WV, not known. Then we are given the acceleration due to gravity, G, 10 meter per second square. You are given density of water. Density of water, D of water is given, or you use rho, is given to be 1 kilogram per meter cube. But the question says volume of water is equal to volume of, so we can now say volume of water displaced, volume working out, volume of water displaced, that's V water, equals half of volume of object. Volume of water displaced equals half the volume of object. Half the volume of object. I have given that here. Then you now go on to work it out. From what you have written here, you can proceed. What is the volume of object? That will be half times 60. And that will give you this cancel 30 centimeter cube. Then that will be 3.0 times 10 to the minus 5 meter cube. That is the volume of water displaced. Very simple. Because you have introduced all the parameters here, you can now go on to work like this. Please and please, do it the way you are asked to do it. You are not coming here to come and it's not social gathering. Every information will make across to you. Please, you cannot do it the way you like or the way you want to do it. Now, you want to put the value. Number one, you have to calculate the volume of water displayed. That is done now. Looking at this work, your work is already self-explanatory. The next one is across on the object. Across on the object, we know. You must have listed the across here. But even if you don't do that, you have Roman figure 2. We need across. Across you. Not know. That's Roman figure 2. But from what we said earlier, across equals density of water, volume of water displaced times G. That was what you are taught. So density of water will now be 1,000. Volume of water displaced 3.0 times 10 raised to the minus times 10. Then how do we solve? How do we solve this without calculator? Please and please, I have done with training you or teaching you how to work without calculator. As this one is, you can quickly turn it to standard form, and that will become 1.0 times 10 raised to the 3 times 3.0 times 10 raised to the minus 5 times 10. So if you add 10 raised to the 1, 10 raised to the 3, that's 3 plus 1, that's 4. Then minus 5. You are going to have 1.0 times 3.0 times 10 raised to the 4 minus 5. 4 minus 5 is minus 1. So everything becomes 3.0 times 10 raised to the minus 1 Newton. In other words, it becomes 0.3 Newton. That is the across. You are looking for the across, and that will be the across on the object. Principle of flotation. The principle of flotation states that the weight of floating object will be equal to the across. Across equals, that's from figure 3 now. We are looking for mass of the object. An object is referred to as floating object. Object is referred to as floating object because part of it is above the liquid. So floating object, that's W this. So we can now say across equals WF, which is the same thing as MFG. We are looking for this. Our across is 0.3 Newton equals to mass we are looking for times 10. Therefore, mass equals to 0.3 all over 10, and that gives you 0.03 kilogram. 0.03 kilogram. 0.03 kilogram. That is the mass of the object you are asked to calculate. And finally, you are asked to calculate the density. Just like we said, the next one is finding the density. Density of the object now is equal to mass of the object. Mass of the object all over volume of the object. The mass of object we know will be equal to the across. We already calculated it. Wait, that's 0.03 kilogram all over volume of the object. Not volume of liquid display, so it's going to be volume of the object, which is 6.0 times 10 raised by minus 5 meter cube. So how do we do this? You don't need to press calculator here. Turn the above to standard form. 3.0 times 10 raised by minus 2 divided by 6.0 times 10 raised by minus 5. If this one goes on, become plus 5. So you are having 3 here, 1, 3 here, 3 here, 1, 3 here, 2. So we are having 1 over 2 times 10 raised to power minus 2 times 10 raised to power 5. So everything becomes 1 times 10 raised to power 2 minus 2 plus 5. That's 3 divided by 2. So everything is 1 times 10 raised to power 3 all over 2. That's 1,000 divided by 2. That's 500 kilograms per meter cube. Any question? Write what you want to write. Another marker. Louder. Don't look at somebody's, just look straight to the board and speak out. Please clap for him. Hydrometer is a device that can be used to determine the relative density of what? Could be acid, could be any liquid. Can be used to measure the relative density of a liquid. That's the instrument we use to. And where do we see this hydrometer? If you see those battery charger, the roadside battery charger, we have it. If you are going home and you see where they are charging battery, you see the person called battery charger. Go to him. Please, where is the hydrometer? If he doesn't know what we call hydrometer, just what they use to check the acid, we will show you the instrument. We have hydrometer is used to measure the relative density of an acid or of a liquid. So please and please, if you come across a question under density you cannot solve, be it JAM, NECO or WAEC, bring that question to the class. Or you send the question to me on WhatsApp. But if you send the question, you give me a call so that we know that you drop a question you need attention to. And don't just drop the question without showing me your trial. I must know extent you understand that questions. If the concept, I believe you have been taught the concept now. With concept, you should be able to solve every question under density to certain level. So you have a question, solve it the way you understand, forward it to me. Then I will see what I can do. If you don't want to talk in the class, or you can also do something, work it out, write the question, work it out, submit that to me. One of the classes, I will go through, I may not disturb in the class, I will go through it and correct your working and send it back to you. If that is what you want, that will still be welcome. It's not only density, every other topic that we've done, or it's not even the only topic we have done. If you have any question in physics, posing problem to you, write the question. But I will not want you to just leave the question that you have not been taught the concept. If I give the correction, you may not understand. That's why we want you to show the extent of your understanding, so that if the correction is made, you easily grasp it. I hope I'm communicating. You have very limited time. You already know the timetable, when the lesson or the lesson is going to be. We still have a long way to go in physics. But nevertheless, I will rush you through so that we can touch some other part. That the only fear I have, I've said it today. Every information you are giving, you are not taking it seriously. That's the only fear. What type of pressure do we know? We want to look at pressure. We want to talk about atmospheric pressure. We want to talk about gas pressure and the instrument used to measure them. The first one is general pressure, after which we move down to atmospheric pressure, and we also talk about gas pressure. Now, what is pressure? Yes.
Pressure is the perpendicular force acting per unit area on the surface.
Okay. Yes, I can see some other hands up. What is pressure? Somebody puts up the hands here. Yes, let's hear you. Sit and talk loud.
Force exerted
On the
on the unit area.
louder.
It is the force exerted
On a unit.
area.
Pressure can be defined. Just simply say pressure can be defined as force per normal area. This is pressure. Pressure equals force per normal area. Normal is very important. Normal is very important. It can also be defined. Okay, you can say P equals F over A. You can say where, if you have it this way, you can say where P equals pressure and F equals force, then A is normal area. Please, the word normal must be pulled. Very important. If you just write force per area, the other thing you are defining. You know, when we say tensor stress is also force per area. But what type of area in that case? Cross-sectional area. You have to qualify the area. It's not just force per area. If you want to define tensor stress, it is force per cross-sectional area. But this one is force per normal area, usually base area. So we can also, from this statement, we can say pressure is directly proportional to force. Pressure is highly proportional to force. 2. Pressure is inversely proportional. Look at this. Pressure is highly proportional to the force. What does that mean? You see my weight and I wear flat shoes. The bigger my weight, the larger the pressure exert on the floor. That's what it means. So we can also express pressure can be expressed as weight per area. The larger the weight, the larger the pressure exert on the floor. The smaller the weight, the smaller the pressure exert on the floor. That's why we say pressure is highly proportional to the weight of an object. If your weight is so large, you exert large pressure on the floor. But if your weight is small, then you exert small pressure on the floor. Is that clear? Now, if you have area, as I'm standing, you measure the area my body is in contact with the floor. How do we know the area? Just map out the position of my feet. That's the area my feet is in contact with the floor. The pressure I exert on the floor now will be smaller than when I use only one foot to stand on the floor. When one foot is used to stand on the floor, the area has decreased, and the smaller the area, the bigger the pressure. If I decide to stand on the toes, the area is reducing, and as the area is reducing, pressure is increasing, because area in contact is inversely proportional to the pressure. The larger the area, the smaller the pressure. The smaller the area, the larger the pressure. That's why we say that is inversely proportional to the pressure exerted on the floor. Is that clear?
Yes, sir.
Now, I don't know if any of you has experienced fetching water from the well
Yes.
with a drawer.
Yeah.
You will notice that when you use trine, you all know trine. Yes. You attach that to the drawer and you use it to fetch water from the well. It will be so painful to your hand because the trine is very tiny. So if you use it to draw water, it will be so painful to your hand. But if you use belts, they are rope like belts. You attach that rope to the drawer. You fetch from the well with ease because the belt is wider than the trine. The pace in your hands reduces. Do you understand what I'm saying? That is in line with what we said, that the area is the pressure is inversely proportional to the area. Some of your bags you are carrying about, they put something like this on the shoulder that you put on the shoulder to reduce the pressure exert on your shoulder. That's why the manufacturer puts a wider space that you put on your shoulder. If that wider is not put, the pressure that bag will exert on your shoulder will be larger than when that flat something is put. Do you get what we are making across to you? That one is simply because the area, when the belt is put, the area exerts on your shoulder, the area of the belt is smaller than that of the part they put on the handle of the bags to make or to reduce the pressure exert on your shoulder. That increases the area in contact with your body. And you know, pressure is inversely proportional to the area. So therefore, that will reduce the pressure exert on your shoulder. Am I communicating?
Yes.
This thing should be clear to you. I was saying that it's a jump question, but I don't know the year. When they will say, at what position will you exert the largest pressure? Is it when the person stands on the 2 feet? When he prostrate on the floor? When he use one side to lie on the floor? Or when he use 1 feet? Or when he use a finger? You know, you can use a finger to stand. Your head on the plan, this will hold you. So when do you think the largest pressure will be exerted on the floor? When you use a finger, that's it. The smaller the area in contact, the larger the pressure. Is that taken for a solid? Good. So the pressure is measured in Pascal. What's the unit of pressure? Pascal. Then when we say Pascal, 1 Newton meter is equal to 1 Pascal. 1 Newton meter per meter squared is equal to 1 Pascal. PA. Newton per meter. Newton comes from the force. Meter comes from the area. That will be Newton per meter, not Newton meter. So that is Pascal. Now, the bigger unit of Pascal is bar. BAR. That's bar. So, and we have 10 raised to power 5 Pascal. 10 raised to power 5 Pascal is equal to 1 bar. Just like when you have kilogram, you have megagram. When you are talking of 10 raised to power 5 Pascal, that's equal to 1 bar. So we can always give the unit of pressure in bar, in Pascal, and so on. Is that clear? Newton per centimeter squared, that is Pascal. So, as a reminder, you can say 1 centimeter squared to meter squared. What do? You divide by. That's it. Please and please, any area given needs to be converted in centimeter squared must be changed to meter squared, because the force will be given in Newton, and Newton is the SI unit of force. So area in most cases will be given in centimeter squared. It is your responsibility to change it to, and it's simple. You are taught all this during the camping. Go and revise that. So that is that. Wait, when we say Pascal and this, the next thing we want to look at is what is the dimension of pressure. I'm glad to inform you that dimension of pressure, dimension of tensile stress, and dimension of Young modulus are the same. I repeat, jump student, dimension of tensile stress, Young modulus, and pressure are the same. You can come across which of the following quantity have the same dimension with pressure. I've given it to you. Dimension of pressure, let's say pressure, then tensile stress, and Young modulus have the same dimension. They have the same dimension. And what is that dimension all about? If I say dimension of pressure, I will put this pressure. That's dimension of pressure. Dimension of pressure will now give us dimension of force. This is dimension of force all over dimension of area. This symbol is dimension of pressure equal dimension of force all over dimension of area. Do we understand? How do we give dimension of force? Dimension of force is capital letter M, L, T raised to a minus 2. Dimension of area is L squared. You now simplify this. You simplify this. So, this will cancel one of these. So we are having capital letter M, L raised by minus 1, T raised by minus 2. That is the dimension of pressure, Young modulus, and tensile stress. The other physical quantities that have the same dimension. Note it. Work, energy, and moment of force. Okay, 4. Those other ones that you can notice somewhere, where would I put that? So you can say work, energy, then you have moment of force. Then you can say torque. All these 4. Torque is also a moment. Moment of what? Moment of couple force. Couple. Torque, moment, force, work, energy, they have the same dimension. Any of these 4, what is their dimension? Of course, dimension of work. If you are looking for dimension of work, dimension will be equal to dimension of force times dimension of displacement. That's it. And force is MLT raised by minus times L. So, and that will give you ML squared T raised by minus 2. That's dimension of work. And it goes to dimension of energy, is dimension of moment of force, dimension of torque. Do we understand this? Yes. So, take note of that. We are still under pressure by the solid. Liquid or fluid also exert pressure. How do we determine the pressure exert on the floor? So, and that leads us to pressure in the fluid. 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 What is the weight of the liquid above? Weight of the liquid above divided by the base area. How do we get that? This, since weight equals mg, since weight equals mg, therefore pressure can be mg all over A, where this is weight of the liquid. You can simply say where W equals weight of fluid, then A is base area of the vessel. Base area of the vessel can be that. The fluid is contained in a liquid and a container. The weight of the liquid or fluid can be this. So you turn it to be this. Also, we know that volume, density equals mass per volume. If density is equal to mass per volume, then we can say mass equals density times volume. So mass is equal to density times volume. That's volume of the fluid, density of the fluid. So we can now say pressure equals density of the fluid times volume of the fluid times G all over A. That's it. The fluid above. And we know the volume. The other time we talk about how volume can be determined, especially for irregular shape. We said the area of the base area times height, base area times height. So since volume equals base area times height, for irregular, you've been taught this. Volume is AH. Therefore, we can say, pressure can be density of the fluid. Instead of volume now, we have area times H of the fluid times G all over A. This A will cancel this A. Therefore, we can simply say, if A cancels A, you can now have pressure in fluid. Pressure in fluid. Density of fluid, height of fluid times G. That is the formula for pressure in a fluid, where P equals pressure in the fluid. Pressure in the fluid Then this one stands for density of the fluid. Density of the fluid. Then G stands for acceleration due to gravity. So, what are we saying? The height of the liquid above a pond determines the pressure. Let's assume this is a tank of water. If somebody sinks to this level, the pressure this person will experience here will be different from the pressure the person here will experience. The pressure the person here experience will be different from pressure the person at the floor experience. Why? The depth. When we say density of the fluid, then we need H. H is equals to depth. We call it depth of the fluid. Or we can say height. We can call it height of the fluid above. The height of the liquid above. Depth you sink to. That's what we mean by H stands for the depth you sink to. Or you can refer to as the height of liquid above you will determine your density. Do we understand this? Now, let's say you have a container. And it's closed. You fill the water or liquid to this end. You have water. The water is there. Now you pick a pond here. Ask what is the pressure at that pond A. You have another pond here. You call it pond B. You have another pond here. You call it pond C. So if you want to determine the pressure here, this is a close. You are going to have what is the height of the liquid above. This is H1. When you want to calculate this, you need the height of the liquid above here. This is H2. You need this one. You need to calculate height of this. This is H3. The pressure at A, PA, will become density of the liquid times H1 times G. That will give you the pressure here. The pressure here will be pressure at B equals density H2G. Whereas the pressure here will be pressure at C equals density H3G. For a closed container. Is that clear? But if it's an open container, you have open container now. It's still the same way. This is open to where? Atmosphere. So it means it's just like a case of somebody, you lift up the chair you are sitting on, you stand up on the chair, and you lift the chair up. You ask somebody to put his or her leg under the chair. If your friend puts his or her leg under the chair, looking at you, by the time you attempt to sit on the chair, what happens? I'm sure that person will not say because you are his friend or her friend, you will let her leg be under the chair you want to sit upon. Haven't imagined how painful it will be, because it is not going to, even if you put the chair on his or her leg, he or she may be smiling, but by the time you attempt to sit on the chair, I'm sure he or she will not allow his or her leg to be under the chair you want to sit upon. Why? Because You don't need to be in physics class before you know that the weight of that person will be added to the weight of the chair on your leg. Do you understand that? So it means the pressure, atmospheric pressure, will be applied to the surface of the liquid here. Atmospheric pressure. We are going to talk about that. Atmospheric pressure. Atmospheric pressure is exerted on every object, be it solid or liquid. Atmospheric pressure is exerted on every object, be it liquid or solid, even gas. If you fetch water into a cup, put it on the table you want to drink. On the surface of that water, atmospheric pressure is acting on it. On you yourself, as you expose yourself to atmosphere, the pressure is exerted on you. What is that pressure? They are weights of all gases, weights of all water vapor, gases, mixture of air in the atmosphere. Their weight is exerted on every object on ground, on the earth. So the weight of all particles above us, you know, we have mixture of gases above us, water vapor is there, dust and particles in this atmosphere. All these exert pressure on us. That is, their weight acting on us is the pressure they exert on us. They exert pressure on every object, either solid or liquid, unless the object is not exposed. Like that's why I said this one is closed. Because it is closed, it's not open to atmosphere. The pressure of atmosphere may not be felt here, depending on this container. But this one is, if you sink to this level, there are two pressures that will be felt here. Pressure due to the fluid above, that's, this may be H1, plus atmospheric pressure. If I want to calculate the pressure here now, I will say pressure equals atmospheric pressure plus pressure due to the level of the liquid. Look at those people. Now, atmospheric pressure is the pressure above the liquid. Pressure due to the level of the liquid from here to here will be calculated, and that will be atmospheric pressure plus density of the liquid, H1 and G will be added to atmospheric pressure at this point, because this is open to atmosphere. Now, if you sink to this level, this may be from here to here, you have H2 here, or HB. Let's call this one HB because this point is point B. Let this one be point A, HA, because this is A. So we now refer to this one as HA at point A. At point B, you calculate the pressure here. Pressure will be atmospheric pressure plus pressure due to the level of the liquid, which will be atmospheric pressure plus density of the liquid, then HBG. This is jam-like question. So if you want to calculate the pressure at any given point in the fluid, you have to consider if the container is open to atmosphere. You have to consider the atmospheric pressure plus the pressure due to the liquid above. Depends on the depth in that container that will determine the pressure, the liquid, the pressure at that point you will feel. Is that clear? Let's quickly now talk about properties. Property of fluid. Pressure in the fluid. What are the properties of pressure? The pressure in fluid. Properties of pressure in fluid. Have you heard of that before? Yes? Pressure at any point in fluid are they act equally in all directions, not in the same direction. They act equally in all directions. They act equally. Please give it to him. Clap for him. Pressure at any point act equally in all directions. Put it down. 1. Pressure at any point in fluid are transmitted or act equally or are transmitted, transmission in all directions, in all directions. And what does that mean? Let me show you that quickly. This is the fluid. The pressure at any point, pick this point. They are transmitted equally or acted equally. You can use the word transmitted equally in all directions. So the pressure here at this point may have downward, may have upward, may have this way, equally in all directions. That's what it means. You have simple experiment to show that the pressure act equally. They act equally in all directions at any point. What does that mean to you? How do you know that they are transmitted equally in all directions? If you take a sachet of water, do you know what you call sachet of water? You buy pure water, put it on the table. Now, punch it with a needle. You punch it with a needle. Remove the needle. The water may not gush out, but try to press the side. You are pressing the side of the sachet of water that is punched. So you press the side. When you press the side of the sachet, what do you experience? Why does it gush out upward? You are pressing sideways. One will expect the pressure you exert to go this way. Why is it that the water is now gushing vertically upward? You are pressing sideways. It's gushing vertically upward. Okay, remove your hand from this side. Now press down. Press the sachet of water down. When you press the sachet of water down, where will the water go to? But your pressure is downward. How come the water is gushing vertically upward? Because any pressure exerted to any direction, it will be transmitted equally through all directions. There is no direction you may apply the pressure to. In the fluid, it will transmit it equally to all directions. Is that clear? If you punch the sideway, you punch the sideway of the sachet of water and you press up here, you will see the water will gush out this way. Am I communicating? That confirms that pressure in the fluid are transmitted equally in all directions. Is that taken?
Yes.
Good. Now, what other points can we state? Other property. Only one person can give one. The others? Yes?
The pressure at all points. The pressure at all points at the same direction within the liquid at the same.
Again?
The pressure at all points in the same level within the liquid at the same.
Okay, that's another good property. But do you understand what he said?
No.
The pressure are the same plane. The same plane. What do you mean by plane? Floor now is a plane. That means the pressure at the point I'm standing, if I move to the back, it is going to be the same. The pressure here will be the same thing with the pressure at the back, in the same plane. Or I take a plank and I make another plane. to the other window there, I put a plant. So from above to that level plane, the pressure at this point to this plane, if I go to the back from up to the same plane, the pressure will be the same. Do you understand? In other words, what it's trying to say in essence is, in the same liquid, the pressure at the same plane, the pressure at the same plane are equal. Why are they in the same plane? Their H are the same. Pressure in the same, number 2. So, pressure at the same plane in the same liquid or fluid are the same. That means pressure at the same level. Pressure at the same level are the same. That's what it means. So if you sink, let's say you have a container like this, and you find yourself in the liquid here, and you sink from the surface of the liquid, down to this, you measure 5 meters. You come here, you measure 5 meters. From here to here is 5 meters. From here to here is also 5 meters. So all the 5 meters, they all have 5 meters to their core. That means the pressure here will be equal to the pressure here because they are in the same plane. They are in the same level. Pressure in the same level. That's what it means. Are the same. Of course, in the same liquid. Do we understand that?
Yes, sir.
But in the same but different liquid, they will not be the same. If you have 5 meters in water and you sink to 5 meters in mercury, 5 meters in water, the pressure at that 5 meters will not be the same pressure at 5 meters in mercury. That one is different liquid. But if it's still in the same liquid, 5 meters below, we always give the same pressure at that point. Is that clear?
Yes, sir.
Okay. Yes, which other one? Before I had my own. Yes. Yes. At time. Pressure is also directly proportional to the depth of the liquid. Right from the formula we can see that pressure is directly proportional to the depth. That is the height of the liquid above. The larger the height of the liquid above, the larger the pressure. And you can demonstrate this by looking for a can or a container. If you drill and you fill the container with liquid, let's say you have a jar like this, and you fill the jar with water. You drill a hole here, you drill a hole here, and you drill a hole here, and you drill a hole here. So, of all, the pressure of water here will be very close. The pressure here, the pressure of the water coming will be larger here. The lesser here, the pressure here will be longer than this. The highest will be this. When you fill this with water, the water coming out, although you set it, you stagger the hole so that the water will not touch each other. You stagger it, just like a container. You drill part here, drill somewhere here, you stagger the hole. You will now see that the pressure will be more with the hole below, because that's where you have the highest pressure. Do we understand that? So we have given 3 or 4 properties. You can add more. So these are properties of fluid in liquid. Very important, and we also make use of them in calculations. Is that taken? Yes. Good. Now, atmospheric pressure. What do we have? Already given you the information about atmospheric and the atmosphere. from GS3, if I'm not mistaken, you are taught the mixture. In chemistry, you are also taught air, mixture of. Can you tell us some of the gases you find in the air that are made up of air? Yes. Louder. Nitrogen. Yes. Which other one? Yes. Oxygen. Yes. Louder. At least we are able to mention 2 or 3 gases now that is made up of the air. And we also have water vapor. Aside that, you have what we breathe out contributed to the pressure exert on you, carbon dioxide. Even though the plant made use of it, and so, but at least you still have extra in the atmosphere. We have water vapor, we have particle, we have other gases that are in the atmosphere. All these are weights above us. All these are weights acting on us. And when we say weight all over area in contact with us, it becomes pressure on us. And that's why we refer to that as atmospheric pressure. Atmospheric pressure is the pressure exerted on every object on Earth by the atmosphere. All particles in atmosphere, all water vapor, all other gases in the atmosphere which we cannot see, all particles in the atmosphere we cannot see, have their own weight. Just we say fluid. Fluid is liquid and gas. And what we have in the atmosphere is mixture of gases. Water vapor is also gas. So they have their own weight because they occupy space, and they have their own weight. The weight is applied or acted on us, and that is what is referred to as atmospheric pressure. Pressure exerted on us by the atmosphere is now known as atmospheric pressure. Is that clear? Everything, be it liquid or solid, that is exposed to atmosphere, this pressure will be on it. Now, how do we now calculate this pressure? Or what do we use to measure this pressure? The pressure that we call atmospheric pressure. The instrument that can be used to measure, okay, let me ask, what is the instrument we use to measure atmospheric pressure, and how does it look like? Atmospheric pressure, what is the device that can be used to measure atmospheric pressure, and how does it look like? Anyway, our time is fast spent. Have you heard of barometer before? Yes, we have different types of barometer. But when we say barometer is an instrument that can be used. What is the noise all about? Is barometer funny to you? Or you have not heard that before? Now, we use barometer to measure atmospheric pressure. And I'm sure in your laboratory in school, your physician can show you barometer if you have not seen it before. You can go and ask the teacher, you want to see how barometer looks like. And your teacher will try for you here now. You can construct barometer yourself. If you want to construct barometer, you need a narrow glass tube, a meter long glass tube. So you have the glass tube like this. Barometer. So you need a narrow glass tube like this. It could be a meter long. That's 100 centimeter. You need a reservoir. You need a reservoir like this, and you need mercury. You need mercury. Mercury you need will be poured into the reservoir. Mercury will be poured into this reservoir. So we refer to this one as mercury. We have this as mercury. Now, how do we construct barometer? You fill this a meter long. Don't forget I said from here to here can be 1.0 meter or 100 centimeter long. You fill this one to almost 3/4, which is about 75. Fill it to 75 with mercury. When you want to do this, you wear hand gloves. You wear hand gloves to do so. You fill the narrow tube to 3/4 and you jack it. You jack it away. Put your hands. You must have worn hand gloves. Put your hands on top of the tube and jack this mercury inside the glass tube. Why do you need to jack? Can someone tell me why the jacking is needed? You jack in order to remove air bubble that may have been trapped inside. Air bubble that might have been trapped inside here needs to be removed by jacking it. Remember, you feed this one to 3/4. So when you cover the end of the tube and you jack for some time, the air bubble that might have been trapped when you are pouring the mercury into the tube will get out. It come to the top here. The air bubble that might have been trapped inside will come to the top. So you jack very well until you are convinced that there may not be any air bubble again. Then remove your hand, fill up the tube with the mercury. That means you pour the mercury to fill to the brim of this. With your glove in your hand, you now inflate the tube carefully into this reservoir. Your hands will enter into the mercury in the reservoir before you open. So the tube will now be inflated into the reservoir like this. So this is what you will now see. So as soon as you remove your hand here, you see the level of the mercury here will drop. And this is what we will now observe. This is what we now call a simple barometer. If you now measure the atmospheric pressure acts here, atmospheric pressure acts here, atmospheric pressure here, atmospheric pressure. So at this level, that because this place is the same level here, that means atmospheric pressure that acted here will be equal to the pressure here. So the pressure at this point equal to the pressure at the same level are the same. Because this is atmosphere, the pressure at this level in the atmosphere are the same. So the pressure here will now be the pressure. What you have above here is empty space. Nothing is there. The gas that would have been there, you have jacked it out. So what you have above here is empty. So the pressure here will now be pressure of the liquid. If you now measure the height of this level from here to here, that's what we refer to as age of mercury, which is equal to 760 millimeter. 7 millimeter height. But because this is mercury, you put Hg. or you write 76 centimeter Hg, or we write 0.76 meter Hg. The height here is equivalent to atmospheric pressure. That is the height atmospheric pressure sustained. The atmospheric pressure sustained the height of mercury equals to 760 millimeter mercury. Hg is the symbol of mercury, or 76 centimeter mercury, or 0.76 meter mercury. That is the height of this liquid, and it's going to be equivalent to atmospheric pressure. So we can simply say atmospheric pressure is equivalent to 760 millimeter Hg. Is that cleared? Is it cleared? Or are you tired? You are sitting, you are tired. What about me? Standing. Okay, it's easier to stand for 3 hours, but it's not easy for you to sit for 3 hours. Now, as I said, in chemistry, and most of the questions, they usually say atmospheric pressure, AP, is 760 mmHg. It is wrong, it is not, but it's equivalent. I have told you pressure is measured in Pascal or Newton per meter or bar. It is not mm, but it's just like somebody wants to buy a car worth of 10 million, and that person has 12 million in his account. He can consider himself to have gotten the car because the car worth 10 million. You already have 12 million in your account. If somebody says you have gotten the car, you can say, yes, I have the car with me, because you have enough money to purchase. So equivalent height that can be converted to atmospheric pressure is 760 mg. 760 mmHg. Hg is the symbol of mercury. Mm is millimeter. So we can convert it to atmospheric pressure. But 760 mmHg is not the actual atmospheric pressure, but that is the height of atmospheric pressure. Am I communicating? How do we now get the atmospheric pressure? In that case, you can now work out atmospheric pressure. You can work out atmospheric pressure. So if I need atmospheric pressure now, I will say atmospheric pressure equals pressure of the mercury times density of mercury times G. That will give me atmospheric pressure. And what is this H? The H is this. The H here is this. Convert this to meter. So it will now be 0.76 meter times density of mercury, 13,600. That's density of mercury times 10. Times 10 now. When you work this one out, that will give you atmospheric pressure in Pascal. So let's work it and see. So what is 0. Well, you can turn this one to fraction to make it simple. 76 all over 100 times 13,600 times 10. 2 0 will go here. So you are now left with 760. 10 times 760. 760 times 136. What do you have? 760 times 136. What is it? 760 times 100 and 103,000. Let somebody talk. 360 Pascal or Newton per meter squared. So we can now change This is atmospheric pressure. Change it to standard form 1.0336 times 10 raised by 1, 2, 3, 4, 5. That is 5 Pascal. That's it. That's atmospheric pressure, which can be called 1.0336 bar. That's actual atmospheric pressure if you really want to. But giving you the height is as good as giving you the atmospheric pressure. That's why in chemistry, when they say standard temperatures and pressure, so they will just give 760. Where atmospheric pressure is needed, we use 760 millimeter. Well, of course, you need to convert it to meter, and you convert it to, you use the density of the mercury to actually work out what the atmospheric pressure is. So that's that. I expect you, when you get back home, to read about density, to read about pressure, and start working exercise. By next class, you may not see me on Wednesday. The chemistry period I use today will be used on Wednesday. The double period I have, the chemistry will make use of it on Wednesday.